Okay, so we continue with problems, and maybe I make some remark on the examination. So, as all you know, the examination would be 18 March. I don't remember time and place. Those who are not here and will not come here, you should make special application in special form that you take your examination at some place. This is announcement for those who are outside of lecture. The link you can find on my model. There will be just one paper for everybody, but it has 9 problems. So first 6 and then 3 additional. So those who are take the, I don't remember which number, 5-point course, you should solve only first 6 problems. Don't this you are not interested. Those who have the course 7 and 5 points, you have to go through all 9 problems. The last 3 problems are usually theoretical. Theoretical problem. Here is also one problem which is theoretical. So 5 problems are practical. This is the structure of exam. For 5 points, to pass examination, each problem gives max 5 points. To pass examination for those who have 5 points course, you should select at least 16 points. So it is you pass. If not, you did not pass. For 9-point course, you should select minimal 21 point. Yeah. So there will be no surprise for you. Everything would be as we studied during the course, and now we train with problems. We train, some functions would be changed, integrals would be changed, and so on. So the second examination, those who did not pass this, would be, I hope to check very quickly, so it would be 6 April. 6 April, maybe one think it's too early, but after this, in next week, I think on 13 April, I go to Japan, so it is the third examination will be already in May. But of course, it's better to pass first examination, or at least this 6 April. So this is more or less everything about examination. And now we go back to training in this. We are still in this first block of 5 practical problems, and okay, 5 practical problems. Let us first repeat what we did last lecture, and we go to logarithm z. This function is defined in the following way. If we write z, e phi plus 2pki, and k we can select 0, plus minus 1, plus minus 2, and so on. Minus and plus will give the same, because in fact 2pki plus minus is the same 1. So to rotate k times counterclockwise or clockwise will give the same. But when we take logarithm, this can generate different values. And I think that the last lecture was good remark that it's better write plus minus. So then logarithm is Here should be, of course, absolute value of z, да? Where r is absolute value of z. Then logarithm is usual logarithm of this positive real number plus I, and here is this 5 plus 2pk. So this is logarithm. It is multivariate function. Of course, we can make it one valued if we select, as people tell, different, you can say such terminology, different case, define different branches of logarithm, different branches of logarithm. So we can choose one key, it would be one branch, another key, another. So the principal value correspond to k equals 0. And this principal value sometimes denoted by large logarithm, and it is just logarithm r plus I phi. So principal value when we just select k equal to 0. So then this logarithm is one valued function. It's one valued function. So there is no this multiplicity generated by this k. But typically we consider this multi-valued logarithm, and the question on exam would be about this small multi-valued logarithm. Yeah, so let us now repeat quickly what we did last lecture. For example, let us find logarithm 1 minus pi. Then let us, for example, also recall Euler formula and find sinus hyperbolic of I, cosinus hyperbolic of I. Yeah, so let us do these three problems. And then we go to the next one.
Symbol. Eller vilket där. Ja, så gör man det samma. Ja. Får det se. Ja, people will. People will function. Lämna det så. Oj, jag vill ta det. Ja. Lämna här till målet. Ja, det är en sak. Aj, aj, aj. Jag tycker nog samma som mig. Jo, det blir samma. Ja. Yes. Det är dubbelkoll.
Those who solve this can maybe also would find very modern city. And what is, for example, for co-teacher would be disaster if you try to find a value of negative real number. So the first problem, we can take this answer, but we can also do in different way to take negative angle, this one, so Of course, it will be the same solution. You can take theta equal minus P4. So if you rotate in this direction. So the answer would be yeah. So and you can identify them if we put, for example, k equal 1, we produce this, which is this one. This is, no, let us all, to finish this logarithm, consider logarithm of minus 3. Logarithm of minus 3. So with minus 3 here, its angle is pi. So minus 3 is equal 3 exponent e pi plus 2t pi k. So logarithm of minus 3 equal logarithm 3 plus pi p plus 2p k. K equals 0 plus minus 1 plus minus 2 and so on. So this is about logarithms. And now these are just definitions of cosinus and sinus, hyperbolic and usual. Hyperbolic and usual, sinus and sinus. So we know that sinus hyperbolic x minus divided by 2, then sinus hyperbolic I x minus ex divided x, we don't need x, yeah, divided by 2, and we want to get, we see that it's practically sinus, because we know also that sinus x is equal ex minus ex divided by 2i. So what we need here 2i, but we should also multiply by I, and it would be sinus 1 and multiplied by I. Yeah, sinus I. So we get such formula. That sinus hyperbolic I is equal I usual sinus of 1. Usual sinus of 1.
How are we supposed to know if we're just going to put I inside the formula, or if we're going to put the other form of I, e to the power of I p half instead?
Yeah, it's a good question, but we don't do this. It just what was the comment? The comment was the following. So this is this we did. Sinus I, да? Sinus z, yeah, sinus z, yeah. So by definition, it is ez plus minus ez divided by 2i. You mean what you mean? I understand what you mean. You mean the following. We gave this definition of sinus z. Then you tell, suppose that we use z in the this form plus 2p I k, and we want to put this in exponent. Yeah, it would be not so good, I think, but let us try. I never heard this question, so it is good. It's not bad. that each year, so it would be x for year I z would be this, So it would be exponent I r e theta plus.
I mean, like, where, with the last lecture when we did, the log.
No, now I'm on this. You put me in this. Yeah, okay. You had different question,
No,
but
I wanted to clarify the question, yes.
yeah, then you clarify your question, but now we in also in quite worse situation, yes. So if you at least as I understood the equation, suppose we this is definition in all textbooks. So the end of the story. After this, people don't think anything more. Suppose now we use exponential form for z. Then we put this z into this exponent. Would it be one valued? Okay, I'm not sure that it would be one valued. It would be one valued, of course, because this is again one. No, nothing happened. So with my, I solved my personal problem. Now it's your problem. Yeah, what was your question?
Yeah, because next lecture we had like the logarithm of I,
Mhm.
and then we had to use I in that form to be able to solve that. So I used the same method for the sinus hyperbolic I as well, but
But
guess
here it looks that it would be no problem, that because this exponent in this would not play any role. Yeah, so because exponent is exponent. Yes, if you put this exponent into exponent, nothing bad happen. Yeah. Okay. Good. With this we finish. It was quick recollection what happened last lecture. So now it would be more or less the first question. Of the exam. Now we go to the second question, which was already discussed at the last lecture. That if you have function two variables, this Cauchy-Riemann condition to check whether it's analytic or not. But as I thought, it can be also, and it will be given at exam in more tricky form, that as you know, we can rewrite it as some function of z and z bar. And Cauchy-Riemann condition, in fact, can be written in these variables, which derivatives with respect to this is zero. So function is analytic if and only if it does not depend on the conjugate z. For example, you get such question: fxy is equal x plus e I 10, and here is cosinus exponent I x square plus y square in the degree 10. For example, this function will go. Of course, you can try to check Cauchy-Riemann conditions, and it's also possible, just some calculations, but you can go quicker. Yeah? So you go to these variables. You see that this is z, good. It's good for analyticity. But then you go cosinus exponent I, and here you see that this is z absolute value in the degree 20. And you know that z absolute value, example square, is z conjugate. So this depends on this. So this is not zero, not analytic. On the exam, I made more complicated, so it will be sinus, cosinus, and so on. But the main idea is that, for example, either it would be just this, or it would be z star, then you immediately tell which function is not analytic, without any calculation of partial derivatives and so on. Okay, so it would be the second question. Then we went to some problem which is not so in fact simple, as I understood. Somebody wrote to me email and I change even at exam because it would be too much calculations, too long calculation. This now we're going to Lorentz series and residues. But with integrals over contours, no problem. So you will, I think, calculate integrals over triangle, over rectangle, over circle. It is no problem. Circle, you know how to parameterize. We did this during the lecture. How to parameterize circles. So the problems which I wrote at the end of the last lecture was for such function, more or less, I think, I don't know, precisely this or something similar. No, and here let us write, for example, already we found the roots, it would be quadratic polynomial, but suppose we found its roots, yeah. So it would be this expression, and for example, there is z cube, z cube. The task was to expand into Lorentz series. Lorentz series. No, this task is not so simple. So what you should do, you take, for example, you want to expand everything in the point, there are 3 points, singular points, z0, z1. No, first in the exam you should find the roots, z2. And for example, you want to expand at the point z equals 0. Now, how I would do? I would take this function divided by z cube. It is cosinus is 1 minus x square. So it would be finally, okay, so it would be 1 disappear, and it would be sum, and from 1 to infinity, z minus n plus 1, n plus 1, z in the degree 2n, to get z square as the first term, divided by 2n factorial, and this divided by z cube, So it would have this form, the first coefficient 1/2 divided by z to z plus, you should write this series. No, it would be series with respect to degrees of z already. That's no, let us write this second term. The second term would be with minus. It was z in the degree 4, so it would be z in the degree 1, and divided by 4 factorial, then plus, and so on. So this we can do. Then we have another block. We have this function. One over z minus 1, z minus 2. Now the idea is to represent it as 2 geometric series and find coefficients. So you can just find them. It's not important for us. We can find A and B. And after this, we do usual business with geometric progression. So it is A, and we take minus A, and here would be 1 minus Z. So this is the sum Z in the degree n. Here we do again take minus, it would be minus b, and take also away 2, and it would be 1 divided by 1 minus z divided by 2, it would be n z divided by 2 in the degree n. We can collect them in one series, but then what is not good and what is, no, let us collect them in one series. It would be series n 0 to infinity minus a minus b divided to n plus 1. Maybe minus we put out. Plus. And here is z n. But what is not so nice is then we should multiply this series and this series. In principle, it can be done. You should collect all terms which correspond the same degree. So, but we shall not do this on exam. So this problem would be simplified. So in principle, we can do this, multiply these two series, this by this, and collect, collect everything. There will be nothing which this term would be by itself. It cannot be changed. Z cannot appear in denominator. So 1 over 2z would be, and then would be, for example, z, and near z some coefficient, z square, and z some coefficient which come from multiplication, and so on. Okay. What we will have on the exam? On the exam, we will be interested only in integrals, which we want to calculate by using residual classes. Yeah. So maybe this we destroy, and now sample question for exam. To find integral around, z equal what is the maximum circle which we can take around point 0, this point 1, this point 2, so at least any radius which is less than 1, we can integrate over this circle, and there is just one pole. The degree of this pole is 1, да? Pole of the degree 1. So now we want to calculate integral over this circle of this function fz dz, and we go counterclockwise to this integral. So try to calculate this integral. And in the exam would be also integrals over, we can also take circle around this, calculate this integral z minus 1 equal, 1 is not good because you go to singularity, for example, this one. On the exam is formulated over a circle of any radius which where this Lorentz series converge. Yeah, so z minus 1 equal, for example, 1/2 counterclockwise, and the third is integral z minus 2. They are more or less all very similar integrals. So you should calculate residues. In these points, and this will give you integrals. All singular points are poles of degree 1. So you can use the standard formula how to calculate residue in the pole of degree 1 without expansion in Lorentz series. Okay, so we make break, and after break, so look these problems. Okay, so I hope that those who solved, not we shall now look how it can be done. First of all, maybe not good idea to destroy, but in any event, we see that all these points are poles of the order 1. And there is a formula, and then we'll discuss it a bit. So if Z0 is pole of degree 1, we multiply function by this, if Z, and take limit Z go to Z0. So in our case, or let us get this formula, where we can get this formula. And what is residue? What is residue? Because there is a theoretical question on residue. Residue. It is better to start with Lorentz series. Lorentz series. So Fz can be represented as infinite sum coefficients a n, z in the degree n. Z minus z minus z0 in the degree n. So residue is coefficient a minus 1. A minus 1 per definition residue. So this series can be written some terms here is some a n z minus z0 in the degree n. At some place we have this. So this in the residue is determined that in the denominator is degree z minus z0. And then start with part of series with positive, with non-negative coefficients. So we are interested in this number, Of course, the direct way to calculate residue is just expand into Lorentz series. If it is easy, maybe it is easiest way. If you don't want to take this limit, or if it's not easy to find this limit, maybe sometimes it's easier to expand into Lorentz series. Now it is remarked, if our function has the pole of degree n, let Z0 be a pole of degree n. Or it's better m. So use n for summation. If it is a pole of degree m, then this series start with, it is not from minus infinity. It is not from minus infinity, but it starts with m. Maybe we destroy this function because it's more or less copied, but with degree 4, and this also. So if it is pole of degree m, in fact, our function can be written as sum n from minus m to infinity a n z minus z0 in the degree n. Or if you start, the first term is this one, degree n plus, and here our lovely residue, and then start positive degrees. and so on. And we work only with such functions. Not all functions have the poles, but for calculations, we only work with these functions. Okay, so we're interested in this term. Suppose the m is equal 1, as in our example. So the pole of degree 1. Then how it looks? The Lorentz series. The Lorentz series started precisely with our residue A minus 1, Z minus Z0 plus A0, A1 Z minus Z0 plus and so on. Therefore, how to find this? The idea is very good. The following: we should multiply function by this. So this would disappear and there will be the number. And then it would be always Z minus Z0 in positive degree. And when Z go to Z0, everything disappears. So if I multiply my function Fz, so it will have the form. Here is now nothing. So residue is in the pure form, this number. And here is A0, Z minus Z0 plus A1, Z minus Z0 square, and so on. Now, if I take limit when Z goes to Z0, Z minus Z0 Fz, it would be A minus 1, because all other guys disappear. This goes to 0, this goes to 0, only this preserved. So for pole of degree 1, we use this formula, and this can be even this theoretical question residue for the pole of degree 1. So it is just this answer, yeah, to get this formula. Now, if pole is not of degree 1, so if function has this form, so suppose that our function is not so, and you use this formula for our calculations. Let us use it. For example, now our function was as it was before, 1 minus cosine z, z cube, z minus 1, z minus 2. We know that 1 minus cosine z, it is z squared, so it is in the, let's consider the point z0 equal to 0. Here is the pole of degree 1. Here is the pole of degree 1. So to find residue f is the point 0. We multiply this function by z, so it would be limit z go to 0. So we multiply, let us write z, 1 minus cosine z, divided by z squared, z minus 1, z minus 2. So this disappear. And now we should find z cube. It was z cube here, it was z cube. So it became z squared. So now we should find the limit of, in fact, we are interested in this guy, cosine of z divided by z squared. Now this limit is easy to find by just expanding cosine of z in the Fourier series. Everything disappear, and first term would be precisely z squared divided by 2. So the limit of this guy, z go to 0, is equal 1/2. And here no singularity, so totally this limit is equal 1/2. And if you put here z equals 0, minus 1, minus 2, minus no minus plus, so 2, 1/4. So residue is equal 1/4. If I did not make mistake somewhere. Then integral, if you calculated residue, integral around z equal, for example, 1/2. counterclockwise of our function fz dz is equal to pi I divided by 4 is equal pi I divided by 2. So this is we calculated. In other points, even easier. We multiply in this point, we multiply by z minus 1. In this point, we multiply by z minus 2. Now, in this function, residues of order, there is a pole. If you go to this function, here is z square and there is z4, so this the pole of degree 2. The pole of degree 2. Incoming question, how to calculate residue in the pole of degree 2, 3, 4, and so on. We need generalization of this formula. So this formula works only for n equal 1. We need generalization of this formula. Either you can memorize it or you can derive it from this expression, how the Lorentz series look in the case of pole of degree here should be m, yeah, should be m. Started with m, yeah. Okay, so we do more or less the same as we did here. We multiplied here by z minus z0, and what we can do here, we multiply this. We want that this singularity disappear. So we multiply z minus z0 in the degree m. Fz. What we get? Singularity disappear. It is good. Here, so on a minus 2. And here would be z minus z0. And our lovely residue, it would be a minus 1. And here is degree, it's not z minus 0, but what is here degree? Here would be degree z minus z0 m minus 1 when we divide this by this, and previous would be m minus 2. Plus degrees which are larger than m. Here would be a0 in the degree z minus 0 m, and so on. Now it is clear that simply to take limit is does not work. It is more or less theoretical question which is called residue for the pole. It is precisely the answer for theoretical questions. Residue for the pole of degree higher than 1.
Yeah, I have a question.
Mm-hmm.
When you took limit is z equals to 0, 1 minus cosinus z divided by z is squared. Is it a standard limit? Or is it
No, I don't know. I did this in this way. When we take this limit z go to 0, 1 minus cosinus z divided by z square. No, I don't remember. Maybe they can be L'Hopital and so on, but I do the following. 1 minus, who is cosinus? Cosinus 1 minus z squared divided by 2 plus by 4 factorial and so on. Yeah, I have in mind the Taylor series for cosinus. Yeah,
then I get it.
yeah. So then it would work more or less on the exam. It could be something similar: sinus z divided by z square. You do the same. You understand that sinus started with z. And you don't interested in other terms, yeah, only in the first term, and it would work, yeah.
Okay.
Yeah. Okay. So this method you can use on also on exam. Yeah. Now, how to be here? Just to take limit is meaningless because you get this term and we are not interested in this term. So we want to destroy this. How to destroy this? By derivation. By derivation. So take the derivatives of degree dzm minus 1 of this function z minus z0 in the degree m f z. And what would be here? What would be here? All these guys, they disappear. If we derive this m minus 1 times, it would be 0. So this block disappear due to derivation. Due to derivation. What will be here? Here we differentiate this m minus 1 times. So, and each time appear, no, at first time appear m minus 1, after next differentiation m minus 2, and so on, 1. And finally, it would be nothing. This will disappear. It would be a minus 1. A minus 1. And what happened with these guys? Here would be the same. Here would be a minus 1 factorial, a 0, but it does not, it would be not precisely this, because we start with m here. It would be m and m minus 1 and so on. I think who is the last? The last is square. The last is square. If we differentiate, I think it would be the same. It should be, I think it would be m factorial. It would be m factorial. Yes, it would be m factorial. I suppose. So a0 in any event it will disappear. And it would be first degree. And so on. So now it go, if you take now limit, z go to z0. So we get this, we get here at this part m minus 1 factorial a minus 1. A minus 1. And we get this formula, which maybe you can memorize, but the derivation, but if theoretical question, you should derive. And here limit z go to z0 and degree m minus 1 gives z m minus 1. More or less what we wrote, z minus z0 is the degree m fz. So this is this formula. This is this formula. Fine. I think we can solve this problem. Yeah, we have time. We have time. So now we go to our functions, and we know that this is the pole of degree 2. If we go to our function. And for example, if you want to calculate integral for singular point z equals 0, so we put z 0, 0. And we should, what we should do, we should take limit z go to 0, and here the first derivative of this thing 1 minus cosine z, z4, z minus 1, z minus 2. At the point, limit z go to 0 and prime. And we should multiply it by z squared. the pole of degree 2, so we should multiply by z squared. Yeah. Now that is z2. And then we should find derivative. It takes some time, of course. 1 minus cosine z, z square. Maybe we make something for not to calculate derivative. Not calculate derivative, but in some simple way. Not some simple way. Then all this should be derivative. Yeah. No, maybe. No, I don't see any trick. You should do work. You should calculate that derivative.
I did in another way.
How you did? Yeah.
What I did,
Uh-huh.
I was calculating a minus 2, that a minus 2 term, and then I subtracted from the Lorentz a minus 2 over z squared, and then I can get a minus 1.
Yes. Yes. Yeah.
So
Is it easier?
I thought it was kind of easy.
No, yeah, because this is not so. No, here we see that this formula may be not always so nice. Yes, because derivative of this complex function is so derivative is here. Derivative is here. Yeah. Okay, so it's enough for today. We more or less finish it with complex analysis, and next on Wednesday we go to Fourier series, to partial equality, and then to solution of Cauchy problem with Fourier transform. So on the exam will be this, at least for those who have course 7 and 5 points, it would be solution of Cauchy problem for heat equation with Fourier transform, but with some source which is a bit different from our lecture. Yeah. Yeah.
Inte riktigt förstod vad jag menar, så
Yeah, you can skriva på tavla, ja. You can skriva här, ja. Att folk kan se det. Alltså, vi faktiskt slutade internet, ja.
Så den är våran funktion. 1 minus 2 z.
Square 2.
4.
Ja.
Det är lika med a minus 2 genom z i kvadrat.
Ja.
Används det bara. Och då kalkylerar a minus 2. Den vet hur vi kalkylerar. Det är bara multiplicera med z kvadrat och sen ta gränsvärdet. Jag fick a minus 2 lika med 1/4.
Okej, ja, det är ganska enkelt, ja.
Så då beräknar jag g av x, eller g av z, som är lika med f av z, minus a minus 2 genom z i kvadrat.
Ja, men hur hittar du den?
A minus 2 genom z i kvadrat.
Nej, det har jag rätt, men hur räknar du vidare? Ja.
Så då försvinner det här.
Ja, det försvinner, ja.
Så då får jag a minus 1 genom z plus a0 plus a1 z och så vidare.
Ja, det är korrekt. Ja.
Och nu kan vi beräkna a minus 1.
Men du måste hitta den.
Jo, exakt. Men det är bara subtrahera.
Ja,
a minus 2.
och det fungerar, va?
Jo, exakt.
Okej.
För då får du vet g av z.
Ja.
För du
ser,
om vi lyckas få den här funktionen.
Ja, faktiskt.
Då kan vi få den.
Ja.
Så g av z, det är den här funktionen.
Min bild att det blir också komplicerat.
Nej, det var inte
Nej.
så
Aha.
komplicerat egentligen.
Mhm.
Det var Taylor-utveckling bara
Mhm.
i princip. Så Z minus 1. Och sen minus en fjärdedel.
Fjärdedel av z kvadrat, ja.
Ja, Z i kvadrat. Och sen kommer jag multiplicera med, det var exakt så var det, Z i kvadrat.
Ja.
Och för att få, vet du, våran A minus 1, våran residue, då beräknar vi gränsvärdet. Då Z går mot 0.
Ja, okej, så du behöver inte hitta det här GZ, jag behöver hitta bara gränsvärde, ja.
Jo, exakt,
Ja,
vi
ja.
behöver-
Mhm.
Men G och Z är ju detta.
Ja.
Så vi har redan hittat det. Så gränsvärdet, då Z går mot 0. Så du multiplicerar den med Z, så blir 1 minus 2Z genom Z i kubik. Oj. Z minus 1, Z minus 2. Sen kommer jag göra en
Den-
gemensam
Mhm.
nämnare, så då får jag minus en fjärdedel. Och då blir det Z i kvadrat. Som blir Z,
Minus 1, z minus 2.
exakt, Z minus 1, Z minus 2. Och sen beräkna det här gränsvärdet. Och jag kommer se att termen kommer försvinna om jag Taylor-utvecklar grejen. Så det här är 1 minus 1 plus massa termer av ordning 4. Eller vänta, jag måste tänka. Vi har ju Z i kvadrat typ förstås. Så det är plus Z
Ну, i princip
kvadrat
här du
genom-
placerar z lika med 0, ja. Och skriva att det blir...
Jo, jag kommer expandera här.
Ja. Mhm.
Så då blir det här plus termer av ordning 4.
Ja.
Då har jag minus en fjärdedel. Z upphöjt med 4. Ska det vara. Och sen blir det plus dbq. Det är 3 minus
Men de
Z.
spelar ingen roll.
Det är
Ja, på något
3
sätt.
genom 4.
Ja.
Den här spelar roll faktiskt.
Ja, det spelar roll.
Den spelar roll. Den andra kommer vara, jag vet svaret på den, det kommer vara minus Z i kvadrat genom 2. Så jag får det här gränsvärdet. Z minus 2.
Ja.
Och den här, det är bra att ettorna tar ut varandra.
Ja.
Sen är det bra att Z kvadrat genom 2 tar ut den.
Ja.
Sen här har vi ordning 4.
Mhm.
De har ingen betydelse.
Mhm.
Vi dividerar med Z i kubik
Kubik.
och tar gränsvärdet och Z går mot 0.
Aha,
det här blir-
det är bara den spelar roll.
Exakt,
Mhm.
3 genom 4 genom, och så stoppar jag in 0 här.
Ja.
För Z i kubik tar ut allt. Så det blir minus 1, minus 2 som är lika med 3 genom 8. Så det här är min residues.
Ja.
Ja, minus 1.
Ja. Det är bra idén. Ja, så det är lite lättare än beräkna derivaten. Ja, så det. Mm. Ja, tack mycket.
Känner mig extra smart
Ja.
där.
Mm. Men du är matematiker, da? Du...
Jo,
Ja, det är bra. Ja, du måste göra sådana.
Men jag tänker residues, då tänker jag bara extrahera A minus 1 här. Men det är det enda jag försöker. Eller A minus 1.
Nej, det är idén, det är bra
Så jag
idén, ja.
får